Just as a wrap-up to the last theorem, 242, as a consequence of, it should actually say part C here, our definition of integrability and the integral itself are not affected by sets of measure zero. We made this comment in class and explained why that's true. C says that the integral of f over E union capital F is equal to the integral of f over E if the measure of capital F is equal to 0. It doesn't affect the integral at all, no matter what f is on that set. So it's enough for a function to be defined almost everywhere, and we use this idea in the proof. The second thing here is the new part. If f is bounded and measurable, and the measure of the space is finite, then f is integrable. So bounded and measurable, as long as the measure of the space is finite, implies integrability. That's not too hard to see, because what we have here for B is that we would have that let M be a bound on F, then the absolute value of F is less than or equal to M, but the function M, characteristic function of capital X, that is a constant, function is integrable, since its integral is the integral of M characteristic function of X is just M measure of X, and that's finite because the measure of the space is finite. So f being measurable and absolute value is less than or equal to an integrable function implies that f is integrable, and in fact the integral of f would be less than or equal to the integral of M, which is M measure of E, and that's finite, so that proves the integrability. The converse is false. You can have a function that's unbounded and a set that has infinite measure, and yet the function be integrable. So integrability does not imply the function is bounded, nor does it imply that space has finite measure, or the set you're integrating over has finite measure. So an example of this, I'll just write down an example and you can check out the conclusion. So on the power set of the naturals, let mu of a singleton equal to, let's let it be 1 over 4 to the n if n is even, and 1 if n is odd, like so. So it's 1 for each of the odds, and of course mu of E would be the summation of mu of the singletons that sets for each of the n's that lie in E. That's what we've done before. That's how we define a measure on the power set of the naturals. And then define f on the naturals to be 2 to the n for n even. So it's going to be clearly an unbounded function. When n is odd, define it to be 1 over 2 to the n, odd. And you can check that the integral of f d mu, this is non-negative measurable, so the integral symbol makes sense. It may just be infinite, right? But in this case here, when you take the value of f times the measure of the set, you're actually going to get this summation of 1 over 2 to the n on the naturals, and so that's equal to 1, which is finite. So the converse doesn't hold. You can't assume just because something's integrable that it's bounded, or bounded except on a set of zero measure. That isn't true. That isn't true. Right, okay, so let's move along to the second big limit theorem, the Lebesgue-dominated convergence theorem. Very powerful and useful theorem. There are other limit theorems, but the two that we'll really make the most use of are the monotone convergence theorem and the dominated convergence theorem. I probably won't even mention any others, except maybe by name, to mention that Vitali does have a convergence theorem that is a little more general. In the case of the Lebesgue dominated convergence theorem, we're going to assume that we have a sequence Fn of measurable functions on a set, the space X, and G is another function that we are assuming is integrable. Okay, so the Fn's, we're not assuming that, but for this G, that's going to be our bounding function or dominating function. Then we'll assume that Fn converges almost everywhere to some function f, and that Fn in absolute values is less than or equal to G. So there's the domination right there. Then the consequence is that the limit function is integrable, and the limit of the integral, or the integral of the absolute difference of Fn and f is 0. And finally, that the integral of Fn actually converges to the integral of f. So I do have an error there. I didn't realize that. This should be gone. Right? Just that value. There's no limit over there. Well, it may be true to say that. It's a constant on the right-hand side. So in the proof, I'm going to try to go ahead and sketch this proof out here. It's going to take a little while to do that, but here's what we're going to do first of all. So first, assume Fn converges to f for all x on all of x, not just almost everywhere. And so that's a point-wise, and maybe I should have written it that way. Let me go ahead and do that. Let's assume that Fn of x, in other words, converges to f of x for all x in capital X, not just on a set whose complement is a null set. And absolute Fn of x is less than or equal to g of x for all x in x. Again, what I'm doing is weakening or taking away the almost everywhere condition. I'm using a stronger condition. Right, so let's see what we can get out of this. Well, first of all, this condition here tells us then Fn is integrable, since g is, and Fn is measurable. And also, since f is the limit, f of x in absolute values is less than or equal to g of x for all x in x. And since it's the limit, since f equals the limit of Fn, f is measurable. So this inequality right here implies that f is integrable. Well, that wasn't too bad, right? We already have one consequences right here. Hee hee. Right, now the next one is a little more intricate. And so I'll also note that also by 242, Fn minus f is integrable for all n. All right, we proved that a sum and difference of integrable functions is integrable. So we can actually at least write that integral that we have above here. I am not saying anything about the limit at this stage here, but what I'm going to do is now use the domination property right here. Furthermore, if we look at Fn at x minus f of x, that's less than or equal to absolute Fn of x plus absolute f of x. And each of those is less than or equal to g, so that's less than or equal to 2g of x. right? So 2g of x is greater than or equal to that absolute value right there. We're going to make use of that in the upcoming statement. So that says, hence, 2g minus the absolute value of fn minus f, pointwise, is greater than or equal to 0. So that's a non-negative measurable function for each n. So by phi2, which only applies to non-negative measurable functions, we can write that the integral of the lim inf I'll put a bar under it to write a little less and keep it in a reasonably small spacing here. The lim inf of that, d mu, which I'll omit here, is less than or equal to the lim inf of the integral of 2g minus absolute fn minus f, like so. So I'm going to analyze the two sides separately, and we'll look at how they work out. So on the left-hand side, first of all, we actually have a limit. So the left-hand side, we know that 2g minus fn minus f, like so. Well, the fn is going to f. So that goes to 2g minus 0, which is just 2g pointwise. So that's what we get on the left. So the left-hand side equals the integral of 2g, or 2 times the integral of g. Okay? So that's what we get on the left-hand side. Now we're going to analyze the right-hand side. So the right-hand side, first of all, we can break up the integral. So the right-hand side, then the right-hand side is equal to the lim inf of the integral of 2g, 2g minus the integral of absolute fn minus f, right? Everything is integrable here, and so 242 d allows us to break up the integral like that, okay? So I'll put the bracket here. Now, the thing about this is, the first part here, that is a number, a finite number. And so the lim inf of a sequence, a sum of a constant and a sequence, or a difference, will simply be that constant, integral of 2g, plus the lim inf of what remains. Now there's a minus in front of what remains there, so that's a little tricky, and I'll have to worry about that, right? So we have that right there. That's a plus sign in between the 2g, the integral of 2g, and that lim inf. I didn't know what it was for a second there, but that's what it is. So, okay, that's 2 times the integral of g. I'm going to write that. That's definitely the case. But I want to just think about what is the lim inf of the negative of a sequence. So let's just do that off to the side. Now, the lim inf of the negative of a sequence, like so, is equal to, remember, we can write the lim inf as the sup of the infs, sup inf of minus an. Let's see, I guess I'll put a k there. K greater than or equal to n. You might actually like it better as a, yeah, let's just put it as lim. We know it's that way too. The limit as n goes to infinity of the infima of minus ak as k ranges from n and beyond. Okay, so we know it as this guy, but the infimum of the negative of a sequence is minus the supremum of that sequence. So I'm hoping that you saw that before. Those of you who had 531 from me saw it. I think you actually had to do that as a problem. In fact, I think you had to do this actual whole expression here of the lim inf of a negative or lim sup of a negative. Anyway, now that we have the limit of something here, we can certainly bring the negative out in front and write that as minus the lim sup it will be now of an, right? So this guy comes out in front, and that gives us a lim sup. So the lim inf of the negative of an is minus a lim sup of an. So now let's apply that in the expression above. Hence, the right-hand side equals 2 integral g minus the lim sup of the integral of fn minus f in absolute values, like so. And now if we put these two back together, the left-hand side less than or equal to the right-hand side, thus, since the left-hand side is less than or equal to the right-hand side, we have that 2g is less than or equal to 2g minus the lim sup of absolute fn minus f. Yeah, okay, well, so, well, everything here is, the 2g's are finite, let me put it that way. The 2g's are finite, and so that says that if we cancel, those are 2 integral of g, sorry, 2 integral of g, and the integral of g is finite, so we can cancel that, leaving us with the expression that 0 is less than or equal to minus the lim sup of the absolute fn minus f, and I lost the integral there too, sorry, there you go. Yeah. Now that's curious, because this is lim sup of a non-negative quantity. Now this is exactly the same as saying that is the lim sup of this non-negative sequence is less than or equal to 0, but we know that's greater than or equal to 0. So the lim sup of this non-negative sequence is equal to 0. That means the largest subsequential limit of this non-negative sequence is 0, meaning that it has that it itself must converge to 0. Okay, therefore, the limit, the actual limit now, as n goes to infinity, of the integral of absolute fn minus f is equal to 0. Okay? So there's the next conclusion. And the last conclusion is a consequence of this. Finally, if we look at the integral of the, the difference of the integrals, I want to show that this thing converges to that, right? So I'll look at the difference of them and rewrite that as the absolute value of the integral of the difference of the two functions, like so, and then use the inequality that we developed at the end of 242, I think it was part G, 242G, to write this as less than or equal to the integral of the absolute value of the integrand, but we know that goes to 0 by the last property up here. So the limit of the integral of fn is equal to the integral of f. So another interchange of limit and integral theorem, the dominated convergence theorem. So I think that I will, I think I'll stop this one right here, and then I'll do the last little corollary in a subsequent one.